As you can see, we're busy setting up the apparatus for the grade 10 electric circuit investigations. I'm John McBride.
And I'm Joyce Parker.
And welcome to this set of experiments. Joyce will be demonstrating the procedure that you need to take, and we'll discuss some of the points of the investigation as we're going along. So Joyce, one of the first things that I've got is a question. What is the purpose and the focus of this investigation?
All right. We are going to find out more about the effects of connecting resistors in series and resistors in parallel.
Are the learners doing this practical investigation to determine the effective resistance of resistors in series and parallel?
Oh yes. The learners will determine the values of their effective resistance of the resistors in series and in parallel. They will do so by calculations using formula in order to determine the reliability of the experimental values. But that's not why we're doing this experiment. We're doing this in order to determine that series circuit is a potential divider and that a parallel circuit is a current divider.
So Joyce, there are two very important concepts and learners often forget about them. But let's take a few moments to explain what we mean by that word, potential divider. Here is a diagram of two identical resistors connected in a series. When the switch is closed, the ammeter reads the current through the circuit. The readings on all the ammeters are identical because the same current passes through all the components of a series circuit. The first voltmeter, V1, reads the potential difference across the first resistor. The second voltmeter, V2, reads the potential difference across the second resistor, R2. The voltmeter connected across the cell reads the terminal potential difference across the cell, labeled VT. When the switch is closed, the reading on the ammeter is 2 amps. That tells us that 2 amps passes through the cell, the switch, the ammeter, and the 2 resistors when the switch is closed. Voltmeter 1 reads 10 volts, and the voltmeter across the cell reads 20 volts. So what is the potential difference across the second resistor?
Remember that both resistors are identical, so they have the same resistance. And they both have the same current flowing through them because they are connected in series. So each resistor must have the same potential difference across it.
So do our experimental results agree with these principles?
Well, yes. The total potential difference across the cell is 20 volts. So the potential difference across resistor 1 is 10 volts. So, which means that the potential difference across the second resistor, R2, must also be 10 volts.
A series circuit of 2 identical resistors in series splits the potential difference in half. Half of the PD is applied across the first resistor, and the other half is applied across the second resistor.
It is good to know how to split the potential difference in half by using 2 identical resistors connected in series. But what makes things more interesting is when you add another identical resistor in series. How does the potential difference divide when you have 3 resistors connected in series?
Here is a diagram of 3 identical resistors connected in series. When the switch is closed, the ammeter reads the current through the circuit. The first voltmeter V1 reads the potential difference across the first resistor. V2 reads the potential difference across the resistor R2, and V3 reads the potential difference across resistor R3. The voltmeter VT, connected across the terminals of the battery, reads the terminal potential difference across the battery. When the switch is closed, the reading on the ammeter is 1 amp. That tells us that 1 amp passes through the battery, the switch, the ammeter, and the 3 resistors. Voltmeter 1 reads 3 volts, and the voltmeter across the battery reads 9 volts. So what is the potential difference across the other 2 resistors?
Remember that all of the 3 resistors are identical. They have the same resistance and they have the same current passing through them. So each must have the same potential difference across them.
Do our experimental results agree with these principles?
Well, yes, the total potential difference across the battery is 9 volts. The potential difference across the first resistor is 3 volts. So, the potential difference across the other 2 resistors must be 6 volts. That means that each of these resistors also has a potential difference of 3 volts across it. A series circuit with 3 identical resistors splits the potential difference into 3 equal parts.
1/3 of the PD is applied across the first resistor, and the next third is applied across the second resistor, and the last third is applied across the third resistor. Series circuits are used in many applications in everyday life. Let's consider some practical examples that will help learners to understand the principles that we've just discussed and to see their relevance in everyday life.
Okay, let's say we have a 12 volts battery and a light bulb that works at its full brightness when it's connected to a 4 volt supply. If that light bulb is connected to more than 4 volts, it is likely to blow.
Shall we do it?
Let's do the demonstration.
Okay, so that light bulb is now glowing quite brightly and it's connected to the 4 volt supply. Let's increase the potential difference. And it's getting brighter and brighter, and at 10 volts it's no longer working, it's blown.
Yes, the light bulb can transfer that greater amount of electrical energy per coulomb of charge passing through it. So the little filament inside the light bulb gets so hot that it melts and then snaps, so the light bulb blows.
Let's go back to your example. A 12 volt battery and a light bulb that operates best at 4 volts. We will use a series circuit to sort this problem out. We want to apply 4 volts across the bulb and connect a resistor in series with the bulb to split the potential difference into 4 volts and 8 volts.
The potential difference across the light bulb must be 4 volts and the potential difference across the resistor must be 8 volts. The potential difference across the resistor is twice as much as the potential difference across the light bulb. We need to connect the resistor in series with the bulb so that its resistance is twice as much as the resistance of the light bulb. The potential difference will be divided in the ratio of 1:2, 4 volt to 8 volt. The light bulb will glow at its optimum brightness and it will have its correct operating voltage across it. That's the purpose of many series circuits, to act as a potential difference divider.
Joyce, before going on to discuss the parallel circuit, let's look at the first part of this practical investigation. Let's work through part 1, resistors in series and potential difference dividers.
Okay, learners, it's your turn to take action. Read through part 1 of the practical. Press the pause button so that you have time to read through the entire practical.
Welcome back again. We're working through part 1, resistors in series.
Instead of using a battery, today we're using a power pack, which gives us steady potential difference all the time. We're doing this so that we eliminate any effects of internal resistance in a battery. Batteries can be fresh or they can be well used and so out of energy that they are flat. We want to avoid these effects. So today we are using this power pack to provide a reliable and steady potential difference across our circuit at all times.
So we connect the positive lead from the power pack to the resistor with a crocodile clip.
I love that description of the clip. See the crocodile's teeth?
The first circuit that we set up is a circuit with one resistor in it so that we can calculate its resistance. The positive terminal is connected to the one end of the resistor and the other end of the resistor is connected to the switch.
Well, we don't have a switch here.
Yes, I know. I should have said the connection from the resistor acts as a switch. We connect it to the power pack only when we are ready to take the readings on the meters. And by the way, this power pack has a built-in ammeter and it measures the current passing through it. So we already have an ammeter connected in the circuit.
Okay, now we must connect the first voltmeter across the resistor. We will call this V1. It is connected across R1. And the second voltmeter is connected across the power pack. It reads the potential difference across the battery, which is the same voltage S across the series circuit.
We're done. Let's see if our circuit is working. You've connected that switch, and I'm going to turn on the voltmeter and see if we get readings. If we get readings, then we'll know the circuit is working.
But we'll open the switch again so that the learners can prepare to record the result. Pause now if you need a moment to prepare.
Please close the switch now, Joyce. Let's take the first readings. The circuit is working. The current reading in the circuit over here is 0.41 amperes. The voltmeter reading across the resistor is 4.02. And the voltmeter reading across the terminal of the power pack is 4.0 volts. Now we add another resistor R2, and we do this by putting it into series with resistor 1. All the ammeter and voltmeter connections remain the same. The switch acts from the second resistor to the power pack, so we are ready to take the second set of readings.
Yes, I am closing the switch. And we have current passing through the circuit. The current is 0.2 amps. It's half the value that it was with one resistor. The voltmeter across the resistor R1 is 2.02 volts. It's also half the value that was previously. The voltmeter across the terminals of the power pack reads 4 volts.
The last circuit has 3 identical resistors in series. Resistor 3 is connected to a lead which acts as a switch. Let's connect up and take the final set of readings. The current is reading 0.13. Voltmeter V1 reads 1.34 and a bit. And the voltmeter across the power supply is reading 4.0 volts. Right now, learners, you should have taken down the results on your worksheet. There are a number of questions for you to answer too, such as naming the independent and dependent variables, and also naming the variable which remains fixed during this experiment. We will leave you time to complete the worksheet for part 1 before we begin demonstrating part 2 of this practical investigation. Please press the pause button until you are ready to start part 2. Welcome back to part 2 of the experiment. We will now investigate how a parallel circuit acts as a current divider. The potential difference across a parallel part of a circuit remains constant. It is the current that divides up to pass through each of the branches of the circuit. Let's see how this works by looking at a parallel circuit.
All right, here is a circuit with one light bulb connected across the terminals of a power pack. The voltage across the light bulb is equal to the voltage across the terminals of the power pack. It is equal to 4 volts. The current passing through the power pack is 0.33 amps, and this is the same current passing through the light bulbs, and it is also 0.33 amps.
Now we add an identical light bulb in the parallel circuit. When the switch is closed, both light bulbs shine brightly. The voltage across the power pack is 4.0 volts and the current is 0.69. It's almost doubled. The current has increased. In fact, we can recognize that the bulbs grow equally brightly, so they must have the same current in them. The current through the power pack doubled, and because the second light bulb opened another path for the current to pass through, the main current from the power pack splits equally through each of the identical bulbs. Parallel circuits are current dividers. The current splits up as it passes through each branch of the parallel circuit, and it joins up again to pass through the power pack.
So adding more and more identical light bulbs in parallel simply increases the current in the power pack. All the light bulbs shine equally bright. So when you disconnect one branch of the parallel circuit, the remaining light bulbs continue to glow with the same brightness, and the current through the power pack decreases.
Parallel circuits are especially useful in household wiring because we can turn lights on and off without affecting the other lights in the house. The same is true about electric plug points. The circuit board of your house shows the various circuits connected. For example, the lights, the plugs, the stove, and the geyser. All these circuits are connected in parallel. If the stove is switched off, the other circuits continue working exactly as they should do. All that changes in the main circuit is that there is less current passing from the power supply.
When we attach an extension cord with 10 extra plug points on it to an electric plug, we add 10 appliances to work from one particular point to another. All these extra plug points are wired in parallel to one another so that none of them interfere with any of the others. This extension cord has a little red button which cuts out at currents of more than 15 amps.
These types of extension cords and adapters with safety fuses may cost a little more money, but they can save lives as well. They prevent plug points being overloaded with large currents. Large currents heat up the conducting wires and can cause fires in the home. Why does the current increase when you add more appliances?
A kettle, a toaster, a microwave oven, and a heater are connected to the extension cord. The kettle takes 3 amps, and a toaster and a microwave takes 4 amps each, and the heater takes 5 amps on its maximum setting. The maximum safe current is 15 amps. This extension cord will be overloaded if the heater is operated at maximum power. And just as well because the conducting cord could be overheated. It could be a fire hazard in the home.
Let's move on to setting up and taking readings of the parallel circuit. Learners, we are now working with part 2 of your worksheet.
The first circuit that we set up is a circuit with one resistor in it, so that we can calculate the resistance of resistor R1. First, connect to the power pack, resistor R1. Now, connect to the positive terminal of ammeter A1. Ammeter 1 connects to the negative terminal of the power pack when we close the switch. Ammeter 1 takes the reading of the current through R1. The voltmeter of the power pack reads voltmeter V1 across the resistor and across the whole circuit VT.
We're done. Let's see if our circuit is working. Yes, we've got readings.
We'll open the switch again so that the learners can prepare to record the results. Pause now if you need a moment to prepare. Let's begin taking results for part 2, resistors in parallel. For one resistor, the voltage across the terminals of the resistor and the power pack is 2 volts. The current through the power pack is 0.19 amps, the total current passing through in the circuit. And the current through resistor 1 is 0.194 amps.
We will add one more resistor, R2, in parallel to R1. This means we are adding R2 across R1 to the negative terminal of the ammeter. Taking
readings on the meter, we get 2 volts on the voltmeter, 0.39 amps on the ammeter for the total current in the circuit, and 0.189 amps passing through the first resistor. We add the last resistor in parallel by putting its ends across the 2 resistors. Then we take readings on the meter. The voltmeter reads 2 volts. The current through the power pack is 0.58 amps. and the current through the resistor R1 is 0.194.
Okay, learners, you've taken down the results on your worksheet. There are now more questions for you to answer by yourself in the classroom. This video will end now so that you can complete your work. Hand in the worksheet to your teacher before you leave the classroom.